Good day, viewers. As you know, I am creating some videos that can support teachers of mathematics in helping their learners, helping their pupils make sense of mathematical concepts and their related procedures and processes. And today we're going to look at solving linear equations. Now, how you model a linear equation and how you ask pupils to model a linear equation will very much depend on how you're asking them to think about the numbers and variables that are involved in the equation. And broadly speaking, there are two ways that we can think about numbers or variables, and these are we can think about them as continuous. So perhaps as model them using a length or an area, even a volume. Or we can model them as objects, each separate variable being a defined object, each value being a defined object. Both of these have pros and cons when it comes to equation solving. With linear equations, you might decide that one is better than the other. However, I think both are important because when it comes to larger equation or further equation solving, when we come to look at quadratics, etc., then it requires a mix and a sort of understanding of both ways of making sense of this. So I think it's important for learners to see both views here, even if you tend to prefer working with one than working with the other. So the equation we're going to start off by looking at is the equation 3x plus 2 equals x plus 10. And we can see that on my left-hand side screen here, I've set this up as a bar model. Now, I've drawn this as a bar model rather than using algebra tiles, because if I use algebra tiles, you can see that although I've got 3x plus 2 and x plus 10, those things aren't actually equal in length. And if we're using a length view to sort of model the variables and model the numbers, then the equality comes from the fact that the two lines have equal length. And with algebra tiles, they don't. And this is because as much as we would want to treat the x here as a variable, when we're working concretely, that x has to actually have a fixed length. We can't be stretching that x or whatever else. So unfortunately, because the x has a fixed length here, it's very rare that if we set up a linear equation, that the two parts of that equation, the left-hand expression and the right-hand expression, will actually have the same length when it comes to algebra tiles. But we can draw that using a bar model. And the only thing I'd say is if you're going to have pupils draw bar models to represent equations, and in particular to represent variables and unknowns, then it's a good idea to have them drawn on plain paper rather than on squared paper, because if you draw an x on a squared paper or any variable or unknown on a squared bit of paper, it tends to kind of take on the value of however many squares you draw it, and it can be upsetting and confusing for pupils if it doesn't end up working particularly well. So plain paper is a good idea here. So if I look at my bar model for 3x plus 2 equals x plus 10, then I'm trying to find the value of x that makes these two lengths equal, that makes the top length and the bottom length equal. That's what I mean by solving this equation to find the value of x. Well, I can see here that there's part of these lines that are already equal. There's an x on both lines that are already equal. And so the logic goes, if I were to remove both of those x's, then the remaining lengths on the top and the bottom would still be equal. And of course, symbolically, what we might do there is show that we're going to remove an x from both the top and bottom expression. And some people like to write that underneath the equation. Some people like to write that to the side. It really doesn't matter, but we're removing an x from both expressions, from both the top and bottom line of the equation. And what we have is still equal. So the top expression is now 2x plus 2, and the bottom expression is just 10. But I can also see another part of this that is equal. I can see this 2 is equal to part of this 10. So if this 2 is equal to part of that 10, then I can reduce that 10 in size. And because I've reduced it by 2, the result of that will be 8. And so now I've got these 2's that are equal. And so I can discard those as well. I can say I no longer need to consider those 2's. And so that's me subtracting 2 from both sides of this equation. And that gives me a result of 2x for the top expression has the same length as 8 on the bottom. And so now I'm in the position where, right, well, I know how long 2x's are, and I can use that information to work out how long a single x is. If this is 2x's long, then if I split this 8 into 2 equal parts, then each part will take on the value of 4. And so symbolically, I might show that I'm going to split this into 2 equal parts. And so a single x is equal to 4. And this is how I can model and get learners to model along with me, solving equations by considering their lengths using a bar model. I can even do the same thing here with an equation like 3x minus 2. So where I'm subtracting a constant term rather than adding it. So I'm going to reset up this equation now as 3x minus 2 equals x plus 10. So I'm going to make this have a single part again, and I want that part to be 10, not 410. But I'm going to make that a little bit smaller because I'm going to pop my 2 in there. And so the idea here is this length, the length up to here, is 2 less than 3x. And so that's 3x minus 2. Don't need this one anymore. Okay, so this length here is 3x minus 2. It's 2 less than 3x. And again, that length is equal to x plus 10. And so what I can see now, I can still see that I've got 2 x's that are equal. So I could remove those 2 x's. I can remove an x from the top, and I can remove an x from the bottom. And that, of course, will, as it did, similar to what it did before, leave me with 2x minus 2 equals 10. But of course, I could reimagine this now. Instead of 10 plus 2, I could say, well, I can actually add these together, this 10 plus 2. Now, this is 2x minus 2 equals 10, but it could also be reimagined as 10 plus 2 gives me 2x. So rather than having the 2 plus 2 there, I could take that 10 and resize it by an extra 2, and that, of course, would turn that 10 into 12. And that's me adding 2. And symbolically, that's how I might represent it, to give me 2x equals 12. And then, of course, the final thing, same as I did before, is say, right, well, if I know 2x is 12, then I can now split this 12 into 2 parts. And so each of those parts I will change to half of 12. Each of those parts is 6. Don't need that line in there. So that gives me a single x is 6. And I can do similar things with fractional equations as well. Here I've got a single x, and the equation I want to look at here is x divided by 2 plus 2 equals 5. And so if I'm modelling this, or if I'm asking Lotus to model this, I might start with a single x, and I might say, well, let's split that single x into 2 parts so that each part becomes x over 2. And then let's add 2 to just one of those parts. So it looks like I'm adding it to both, but I'm only adding it to one. And you can see I'm only adding it to one because I can then say, well, then that one of those x plus 2 parts plus 2 is equal to 5. And then I can go much the same way as I did previously. I can say, right, well, this 2 here is part of this 5. Part of this whole 5 is covering that length of 2. So if I copy that length of 2 down, and then I reduce this 5 in size, that 5 will become 3. And it doesn't really matter that the 3 and the 2 look like they're the same size there. I mean, if it does confuse learners with that, then fine. One thing I will say about this as well is when you're dealing with fractional equations, if you're going to deal with it in a bar modeling app such as this, then it's worth just checking that the equation will fit. It can sometimes be difficult to make these all line up when you start splitting them, as I found the first couple of times I tried to record this video. So now I can remove these 2's. I don't need these 2's anymore. So again, I'm symbolically subtracting 2 from both the top and bottom expression, and that gives me a result that x over 2 is equal to 3. And I can see that there, that the length of x over 2 is equal to 3. Well, then if I want to get back to my whole x, that's my whole x, then of course I'm going to need 2 of these. And so I can copy another one of those there. I can't combine these, unfortunately, although I could add another bar with 6 over the top. But if I'm hand drawing this, then I can extend that and rub out that middle line. But we can see that I am having 2 of those, and I have doubled the size of that, and that tells me the single x is double 3, which is 6. Now, where bar modeling and length views in general tend to be not as clear, shall we say, is when we have equations when the value of the variable is going to end up negative. And you can see I've set up one of those down here. I've set up x plus 5 equals 2. Now, I can solve this using bar models, and I can model solving this, but of course the immediate difficulty or the immediate sort of point of contention comes with the fact that this 2 is longer in length than this 5. Now, I can still sort of make sense of that. I can say, well, if part of this 2 has got to be 5, so I can copy that 5 down, then I've got to resize that, and what's the other part going to be? Well, if part of 2 is 5, then the only way that makes sense for the other part is to be negative 3. And so I could discard the 5's, and negative 3 and 5 makes 2. And so that's me subtracting 5 from both sides to leave x equals negative 3. But I'm sure you'd agree that it takes quite a bit of sort of fluency and comfortableness with negative numbers to sort of see that, and to see 5 as part of 2 with the other part as negative 3. We don't get the same problems if we use an object view for these equations. And particularly if we are happy representing negative 2 or minus 2 using negative tiles here. Now, I'm using the equation solver that's set up in MathSpot, and obviously if learners are doing that, they won't have this, but it's easy enough to set it up with tiles on either side of their desk and saying this collection of tiles has to be equal to this collection of tiles. So here I'm going to build that first equation again. 3x plus 2 equals x plus 10 going to move that so it's not in the way of the text. And I'm going to set those equal to each other. I'm going to say I want those two things to be equal to each other. Okay, well, this is now an object view. It's this collection of objects is equal to that collection of objects. There's nothing involved in the length here. And I can do this in much the same way. I could, if I wanted to, remove those 2's from that box and then remove 2 from there, and I could remove x from that box and remove x from there, and that would leave me with 2x equals 8. And then, although I can't make this change, I can see that if I half each of those, the top half is equal to the top half, the bottom half is equal to the bottom half, and so I get x equals 4. Okay. Alternatively, though, I'm going to put these back in. A perhaps nicer way to model that is, rather than physically removing the ones, is to use the negative tiles. Okay. I've covered up my number there a little bit. Is to use the negative tiles, because the negative tiles will help when I want to represent negative variables or negative values. Sorry. And so what I might do here is, rather than removing these 2 ones, say I'm going to bring in 2 negative ones, and they create 0 with these 2 ones, which means I can bring in 2 negative ones on this side as well to retain that balance. And because I've got the 0 pair turned on here, if I wish to, I can actually physically 0 pair those and make them disappear. And I can do the same thing with the x's. I know in the previous one I did it with the x's first. Of course, you'll appreciate it doesn't really matter which way around I do those, and end up in the same position. Now, the reason this is useful is because if I then try and represent the second equation, this one here, 3x minus 2, well, I've got my 3x, but how do I represent minus 2? I can't be exactly taking 2 from the box that isn't there. Well, how I might represent minus 2 is to use the negative tiles. And then I have my x plus 10 again, similar to I had before. And now if I'm trying to solve this, well, because I'm using my negative tiles now, I can straight away remove an x. And then it's, okay, well, what about this negative 2? Well, if I put 2 positive ones in here, and I put 2 positive ones in here, then that's now equal. Although it's saying it's not equal, it definitely is equal. There might be a little bug in the software there. Okay, and then I can do the same thing. I can line these up so that my x's there are equal to the top line, and my x's here are equal to the bottom line. And so I have a single x is equal to 6. Fractional equations, a little bit harder with this again, because concrete tiles, you find it difficult to tear them in half unless you've actually got them in a place where you can physically tear them in half. On the algebra tiles, if we're using an object view for something like x plus 2 equals 5, so not using the equation solver but using the object view, then it is actually possible to split that x in half. It doesn't retitle it, but we can split that x in half, and then we can start dragging in some negative tiles and making the link that if this is equal to that, then the other half will require another 3. So we can do that here with the algebra tiles, but you can't do that unless you've got like paper algebra tiles. However, for the equation solver, we don't get this same issue about lengths because we're not modeling with lengths anymore. So I can quite happily now model x plus 5 equals 2. And I can set those equal to each other. Sorry, that's x plus 6 equals 2. X plus 5 equals 2. I can set those equal to each other. And then I can start looking at, okay, well, to find the value of a single x, I'd want to remove these 5. So I'm going to bring in 5 negative 1s. But having done that to this side, I'd need to also do that here. And there we are, they're back equal. So this is perhaps just a couple of ways that you can use visuals, manipulatives to support the solving of equations. Like I say, I think it's important that learners see both and are familiar enough with both that they can see what's happening there, because I think in other circumstances with, like I say, with quadratic equations, things like that, being able to recognize both will be important there. But if you have a preferred one for linear equations, I don't think it's a huge thing to sort of favor one or the other. Hopefully, that has helped see how you can support learners in making sense of solving linear equations. If you're more interested in manipulatives or interested in more ways of using manipulatives, then please do check out my website, visiblemaths.co.uk, and there you'll find, amongst other things, a link to some samples of my book, Visible Maths, which contains a whole host of hints and tips and ways of working with manipulatives and visuals for stuff from number work all the way up to higher algebra. As always, I'd like to thank mathspot.com and its creator, Jonathan Hall, for the use of the virtual manipulatives here. If you've never been to mathspot.com, then please do make sure you check that out. There is a huge wealth of resources there, not just the virtual manipulatives, but all sorts of things to support teaching of maths. And as ever, I am going to be building these videos up over time. So if you have a particular concept that you think you would like to see explored using manipulatives, then please do get in touch. Thank you very much.